Color is Only as Good as Its Neighbor by Danielle Hawkins. You know those internet debates where people say, oh no, the dress is blue, or oh no, the dress is gold? This is due to a scientific phenomenon called color and contrast theory, or simultaneous color, and understanding it can be a useful skill in art making. Simultaneous color can really be shown in 5 different ways, the first being changing the value of one hue to another. So you see here I've made a gradient of different purple from light to dark. If I took that middle purple shade and I wanted to make it look darker, I would put it next to a lighter color. If I wanted to make it look lighter, I would put it next to a darker color. Now, as you see here, as I zoom in, you can see that on this side, the color looks darker, and on this side, it looks lighter. Here it is again shown with blue. We can really do it with any color. Now I'll draw one in orange. So first I'll take a lighter shade of orange and then a darker one, and then I'll put a mid-tone in the middle, and as you can see, once again, on the side where it's lighter, the color looks darker, and on the side where it's darker, the color looks lighter. The second aspect of simultaneous color theory has to do with changing the intensity of one hue to another hue. This has to do with a color looking more like itself when put next to a color that is nothing like itself. So any colors that are complementary on the color wheel. So red will look more like red next to green than it will next to another red. We can show this again using yellow and blue. So if I put a dull yellow and a dull blue, and I put a brighter yellow on top, the yellow looks more yellow on top of the blue. The third aspect of simultaneous color theory is changing one hue to another hue. This only works with secondary and tertiary colors. Tertiary colors best. So for this example, I've used the secondary color of purple next to the blue, and it looks more like a red purple rather than a blue purple. And I've put it next to red to push it further to blue. So now the purple looks more of a blue purple rather than a red. So as long as the colors are secondary or tertiary, you can really push them in any direction you want to by putting the opposite color next to it. To further show this theory, I'm going to show how to push a yellow-green, more yellow or more green. So we'll start off by taking a yellowy green, and then we're going to want to move it towards the blue, so we're going to grab a yellow. Okay, then we're going to move the green more towards yellow, and to do that, we're going to put some blue around it. Now, as you can see, as soon as the yellow and the blue are both surrounding it, the one surrounded by yellow looks more like a bluey green, and the one surrounded by blue looks more like a yellow green. Whatever you want to do the opposite. The fourth aspect of simultaneous color theory is changing all 4 aspects of color by putting a different color next to it, changing hue, saturation, brightness, and value. In the example, I took a high saturation bright orange against a low saturation dark blue, and with different hues and values. This pushes the turquoise in 4 different ways on either side. As we can see, against the high saturation, high bright orange, the turquoise, which is also on the opposite side of the color spectrum from the orange, looks more like turquoise, but a more low saturated, darker turquoise than on the other side. Whereas with the blue, which is low saturation and darker, and on the same end of the color spectrum as turquoise, we get a brighter, more saturated turquoise, but it's not as strong as a color as it is against orange. And for the example, I made a lime green more dull and desaturated by putting it against a bright saturated red, and more bright saturated by putting it next to a dull and desaturated blue. The fifth and final aspect of simultaneous color theory is injecting color into a gray object. Whatever color you put behind the object is the opposite of what color will be injected into the object. So for red, it'll be green. For green, it'll be red. Now, why are we able to do this? Why are we able to change a color by placing another color next to it? Obviously, we know the color isn't actually physically changing, so why are we perceiving it that way? What actually has to do with the physics of color and the biology of our eyes. Color is a wavelength, and different colors have different wavelengths. The retinas in our eyes have 3 different cones that perceive 3 different wavelengths of color. The short cones perceive blue wavelengths, the medium cones perceive green, and the long cones perceive red. So how are we seeing such a range of colors when our cone cells only pick up those 3 colors? Well, other colors are hitting more than one cone. And our brain is comparing and contrasting that signal to the signals of when it only hits one. For example, yellow is actually hitting the red and green cones, meaning we can perceive yellow either by yellow hitting our eyes or by both red and green waves. This is actually how the pixels on our screen work. If you see yellow on a screen, it is red and green pixels next to each other. Because our eyes see color through comparing and contrasting to understand, our eyes and brain instinctively understand colors based on the colors around it. This is the principle in which George Seurat's pointillism paintings are built, and also the principles in which simultaneous color theory or color and contrast theory. Now, how can we apply this theory practically? Here's an illustration I did of a planter at Toronto Zoo. I used the first principle to change the value of one hue to another by using different values of blue. I then used changing the intensity of a hue by adding an orange highlight to bring out the blueness of the sculpture. I followed that up by changing the blue-green of the plant to a more green by using a bluer shadow. I then added a yellow highlight to the plant to once again change the intensity of a hue. And then finally, I brightened and saturated the whole image by contrasting it with a low saturated, low brightness blue or purple.